it seems pretty obvious, but it does give us a lot of potentials for saving an enormous amount of energy while also providing a whole bunch of new unique products that otherwise we would have to send up. Um, let's see, and that system there was working about 1 to 2 exponents. We were really surprised that there was how much iron and manganese was in this mushroom waste system as well. And we're using these wetland reactors to satisfy CBOD, or chemical and biological oxygen demand, while filtering out the suspended solids. And most of the suspended solids are the CBOD, so getting one is the other. It's just two proxies for the same general cleaning the material. And then after this water is fully cleaned, and this is still a work in progress. I've got to build a whole bunch of advanced oil and grease separators for this system as well. The idea then is to run it through potable. They have you can't really see it here, but there's a big reverse osmosis system. And they turned it on originally 6 or 7 years ago, and it crashed immediately. Just the water was way too nasty, as spec'd by the original workers and the engineers who put it together. They called me in. We got part way there, but now we have to handle the oil and grease. So once again, iterations. It's a process. But so this is more the biological components, but then combining the two. So if you're thinking about regolith, ISRU, and the biotic, say your greenhouse domes, so to speak, where you're using primary productivity to produce plant fibers that then become growth and attachment area for other metabolic pathways. Once again, that's basically what a wetland is and does, as long as it's open to the environment. Now, on Mars, that open environment would be everything it's going through the bathrooms, so to speak. You really don't want to waste that, because those are metabolites. And if you're thinking about Redfield ratios of algae production in the oceans, you're gonna or gee whiz, even just your mom's rose fertilizer of a 10-10-10. You have to be able to get those nutrients from somewhere in order for the microbes to have the available, those basic components of life to even be able to take hold, let alone self-organize. So that's why you can't necessarily have one without the other if you don't do it in a big, messy, heterogeneous waste stream in the first place. You almost shoot yourself in the foot, or at least that's what we're seeing here. Okay, once again, so that's some other reactors I've done. One there in the bottom right corner, then that's the tide pool. Yes, I have used it, and I'm not using it now because it needs a stink pipe. And I ran out of funding to be able to do any sampling, but it's exactly what you would expect. It's a self-organizing wetland bioreactor that is designed to, remediate poo. Just leave it at that. The one directly above it then is a much larger version. That one has not been deployed yet, and I built all those by hand. That's all HDPE. They're heavy. They're not necessarily what I would send up, but when dealing with acid mine drainage remediation, throw anything you want at it. That stuff's food grade. That's why it's important that if you start with the best possible material, and that's so far the best thing I've found, because it's not electrically conductive. And that's a whole other talk of why that you would want it to be electrically conductive, but that's later. Let's see, and then the other picture there in the left corner, that's one of the guys down at Kenneth Square. Then we put a greenhouse covering basically over top of it to increase temperature. At the flow that this system was going, I'm not worried about it being warmer and losing oxygen saturation. We're more worried about just increasing the metabolism overall for the winter. And that's in the Philly area, so it doesn't get that bad cold. It's not like it's Montana or anything like, or Alaska, gee whiz, or the Arctic, but it still gets cold. Let's see here. That's manganese oxide I got from one of my older reactors. That ended up being 85% MnO4, bernacite or ranciaite, with I think it was like 5% strontium in them as well. So that's a biological, we think that's a biological process. Now, it won't occur until all the iron is gone, and I'm still trying to figure that one out. But we also found a fair amount of pyrite in there, and there shouldn't have been any pyrite at all. So I think we're starting to reduce the iron again back into pyrite, and that only just popped into my head 2 days ago. So there's a lot to learn. Okay, so okay, yeah, we're doing all right on time. Okay, so then moving forward now, Briar Fisk, who is another one of the individuals working with Arcology X, he is our subject matter, the SME and lead developer of the Gaia module and operating system. A module is one particular component within the system of the command and control system of a larger self-organizing ECLIS, essentially. And I talked to him just this morning. I'm going to read this. I'm sorry, you're never supposed to do this, but I'm going to do it anyway so I get it correct. But he said in technical terms that the Gaia module, the operating system, is a symbolic neural network that encodes input patterns losslessly and recovers them as such for generic time series predictions to be used in the anticipatory and preemptive mitigation of deviations from goal states in the system. Y'all got that, right? Yeah. I mean, it's taken me a little while, but I mean, what this essentially is, I got one more page, and sorry, this one's boring, and I don't mean to keep reading to you, but it's easier to do it this way. To translate the plant people, it's autonomic homeostasis of a multicellular, multi-metabolic pathway organism, also known as an ecology, but in this case, it's one where the Gaia module takes the afferent sensory input to determine the current state of the system and then compares that against its memory to get the controlled system to where it should be to achieve homeostasis. And then to put it another way, the Gaia module draws from memory to determine pathways, methods of mitigation that engender negative feedback loops to return the system to homeostasis. Now, importantly, we feel this this is within Arcology X, and why I think his work is so important, at least to me personally in my own work, but just in general, it's just really neat stuff because I'm not a computer guy at all. So I love hearing him talk about this stuff. But importantly, we, and that's all of Arcology X, feel this system's advantage is that the wetware hardware doesn't just return to homeostasis, that Gaia predicts from past performance to reduce the chances of positive feedback loops and takes steps to prevent them. So even before it starts happening, it would have already seen the issues long before the triggers even begin to, whatever that state is, that trigger is, before it even gets to that point. I think I'm saying that correctly. They're essentially autonomic functions as opposed to executive functions. And regulation for the hardware. And it's essentially the lizard brain. You know, it's not something that we set the parameters and it says, okay, I'll take care of that. Oh, wait, hold on. This oxygen is going up. So, okay, I know this is going to do this. This is going to do this. So I'll go ahead and just head them out at the pass. That's what it's designed to do. Keywords there are Gaia module, machine learning, time series prediction, and symbolic abstraction of input data. Now, knowing what we know now a little bit about wetlands and self-organization, those different redox steps, that it's a distillation system, and that we want to then take regolith and use our own wastes to continue to process more regolith to then go to an exponential increase in productivity or production, I should say, of the system. That's when we get to this. I'm not going to get too much into this. I pulled this together about 3 or 4 years ago for, it was the Mars Society. I presented with them a couple times. What up, Zub? This is essentially a self-organizing wetland series of bioreactors. That's all the threes there in the middle. The green stuff is our HABs. Manufacturing and the like is the white 4D and 4E. 1C, 1A, 1B over there. The pink stuff, that is regolith. And then you've got an abiotic, partially abiotic system in between the wetlands. So 2A, 2B, and 2C. This was made from Mars, where you have an enormous amount of perchlorate. Perchlorate is a form of a salt. It's also rocket fuel. It's ClO4. O4. There's lots of oxygen available there. We don't have to worry about oxygen when we get up there. It doesn't look like we have to worry about water either, thank goodness. Pretty much anywhere we go nowadays, now that y'all have found out what we're looking for. But once again, I don't want to get too deep into this, but this is the different redox steps, and this is available if anybody would like to take a look at it. Please punch holes in it. I will not be offended if somebody can call me out on some things here. please, peer review, all kinds. But this will be available. Happy to share any of this with you later on. And yeah, thank you. Special thanks to Stuart Nelson, Frank L'Italien, Briar Fisk, who couldn't be with us. Now there's Dr. Dan Tompkins. I'm sure some of you may have met him in the past. Dan talks to everybody. There's S. James Parsons, fellow veteran and good friend of mine, buddy of mine, Stelly, and the Mars Society. Thanks also to Pat Grubbs for finding me. He got a hold of us and let us know that the space ecology group was even a thing. Yeah, right. Yeah, I'm clapping as well. And also, just a quick shout out to Ben Franklin Technology Partners, who helped fund our early work, Penn State University, the Smithsonian Institution, Geosciences, who have done quite a lot for us and turned us on to a lot of the manganese knowledge that we have, and SAP D&C, which is one of our local business developers and incubators here in the Altoona area, and then my info.